A very good morning to one and all. So today's lecture is on power electronics for fax and DGs. So as you all know, in each fax devices, or if you take DGs, the very important part, or you can say there, the heart of that devices which are used there is nothing but the power electronics. And this power electronics is controlled using number of controllers like microcontroller or FPGA based on the application. They form the brain of that. So the whole application, any applications, if you take drives or if you take fax or if you take the distributed generations, all these things, the heart is nothing but your power electronics. So first of all, before going into that application, the very important thing is you have to know the basics of power electronics. What is power electronics? And how is it different from the linear electronics, what we are learning as one of the subject in our curriculum? So first, so how is power electronics distinct from linear electronics? How they are different? So how this field of power electronics came into picture? So here mainly if you see, you can see two things. Power electronics, which is a combination of two fields. One is power engineering and another one is electronics engineering. You can divide them into two. Okay, so first power engineering and electronics engineering. So how will we tell the different things about power engineering and electronics engineering? The first thing if you see is the signal level. In case of power electronics, the signals are at very high voltage and current. And in case of electronics engineering, it is at lower level. So in electronics, I'll tell you, it is maybe say 5 volts or maximum 24 volts. And the amps is in few milliamps, not more than 1 amp. It is very few milliamps. Okay. But in case of power electronics, can you just guess what might be the voltage and the current level? 440, huh? 765 kV. Yeah, it is a little close. You can say, like, what might be the maximum? So there the power level is in gigawatts. So it may be 10,000 kV or higher. Okay, you can see the transmission and distribution side, not the distribution, the transmission side. So it is very high. And can you give a guess about the current? How many amps approximately? 100,000. It is more than 5,000, 7,000 amps. So you can just think a small device withstanding some 10,000 kilovolt and it can carry some 5,000 amps. Just imagine what type of device is required there. So here, in case of power engineering, PPT, in case of power engineering, it is high power level, and in case of electronics, it is at signal level. The next thing, if you see, in case of power engineering, power might be our machines, our fax, and all these things come in power. Okay, and the electronics engineering or the electronics, we see the controller side, like microcontrollers, there, it is the electronics engineering, the op amps, they operate at that. So there, in case of this power engineering, a high efficiency is a very important thing, is it? We want to transmit the power at full efficiency without any losses. That is our main aim in case of machines, or in case of transmission, distribution, any place you take. But in case of electronics engineering, there also it is required. I don't say it is not required, but still that efficiency is not a major concern there. So you're transmitting a signal, it's slightly distorted. You can just, there are different methods to recover it also, but it is not a very big loss there compared to this power engineering. The next thing is, what is the principle between power in power engineering and what is the principle in electronics engineering? So next is the electromagnetic induction. So in case of motor or transformer, the principle is electromagnetic induction. But what is in case of electronic engineering? It is movement of holes and electrons. How the electrons and holes move that. So now can you combine these two fields together and tell me what is power electronics? So some of the properties of power engineering and some of the properties of electronics engineering, we combine to form this power engineering. So let me just say power electronics engineering. So this high power level, high efficiency, movement of holes and electrons, this combination which you can see here is nothing but your power electronics. You're not taking the electromagnetic induction. That is not the principle here. Here it is high power level. We use it at fax and DG. So here high power it has to work. Then high efficiency, it requires high efficiency. And the other thing is, there we are not using electromagnetic induction. The principle here is the movement of holes and electrons. So this is the principle. So these three combination together will form your power electronics. So these three together is nothing but your power electronics as such. Next, we are just taking a simple diode. All of you would have known what is a diode. So here it has a P region and an N region, and it is here reverse bias. So when it is reverse bias, you can see here a depletion layer. Okay, a small depletion layer. This is the depletion layer, which you can see here, and the thickness of the depletion layer will increase depending upon the reverse bias, how much reverse bias you have given. So this is the depletion layer here. This is a simple device. Now, this device, let us assume that it can withstand some 5 volts and some few milliamps, some say 20 milliamps or something. Okay, so now the same device, we want the same device to withstand some say 10 kV and some 5000 amps it has to carry, because this also works in the same principle of movement of holes and electrons only. What magic should we do there so that the same device can carry very high voltage and very high current? So what can we do? Any idea? What can we do, so that the same device can carry now very high voltage and high current? Like it can withstand high voltage and it can carry high current. So it is nothing but doping. We all have learned in electronics this thing, what is doping. So adding impurities to it. What you can do is you can add a trivalent or a pentavalent impurity to it. So automatically that we will see how it is able to carry it. So just let us see. So let us see the PPT. Where, say a diode, simple diode itself I am taking. Okay, so it has a P region. It has a P and a N region. And now this device, we have to make this device carry high voltage. So what I'm going to do is I'm going to introduce one more layer, that is an N minus layer. Okay, so I'm introducing here one more layer, and that layer I'm saying it is N minus. And I will make these two layers as P plus and N plus. So I'm making these two layers as P plus and N plus. Okay, so how will we make these region as P plus and N plus? That is the next thing. So as I already told you, by doping process. So you have to add dopants. So here, when you want to make N minus, you will be adding electrons. More electrons are required. So you will be adding pentavalent. Okay, so we will just see what is that. So doping. What is doping? In this case, what we do, we just add impurities to silicon or germanium. You know, mostly the base of this PN junction, diodes or semiconductor devices, either silicon or germanium, whose valency is 4. Valency electrons are 4. So in this case, here you can see germanium is used, and this germanium, it has 4 electrons, and now you are adding an impurity which is boron to it. So when you add boron to this, see here you can see this is the boron electron. One of the electron here, this is the boron, and here again you have 3 electrons, boron electron, and 1 hole is left. Like here boron is now having only, it's a trivalent, only 3 electrons are there. Similarly, for germanium there are 4. So this is 1, this one is the second one, so this is the third, and this is the 4th. Similarly here also 4 it has. So this one, these are the different electrons. You can see 4 electrons. Similarly in the case of the other one. So now bonds are formed. So here in this case you can see this boron 1 electron and germanium, this will form a bond here. Similarly this is forming a bond, these 2 electrons, and here this is also forming an electron, sorry, the bond here. So what will happen, one electron is here, germanium there are 4 electrons left, and one hole is formed here. So one hole is formed here. So as you add more number of borons, it becomes a hole donation. It becomes a hole donor, and as a result of it, it has more number of holes. So it becomes a P plus region. From P, it becomes P plus. So we will see what is P plus, what is P minus, or what is P. Okay, that range also we'll see. Similarly, in case of phosphorus, phosphorus is having a it's a pentavalent pentavalent element. So there is one extra electron. So when you add phosphorus to it, automatically there are more number of electrons. So it becomes an N minus region. Okay, so this is clear. So now, how will we say what is P plus, what is N minus, or what that we will just see. Before that, we went for semiconductor. For such device, we went to semiconductor. Why don't we use metals or insulators? We should have used metals or insulators also. No? Metals also will conduct. It's very good. You can use this like instead of using this power electronic devices using holes and electrons semiconductor. Why didn't we use this metal or insulators? The reason is, in case of metals, already it is flooded with electrons. It is having 10 to the power 23. Here you can see it is having, metals are having 10 to the power 23 electrons per cubic centimeter. So you can see here it is having around 10 to the power 23 per cubic centimeter electrons. In case of insulators, you say, they are scarce of electrons, only 10 to the power 3 per cubic centimeter. 1 cubic centimeter, if you say, you take only 10 to the power 3 electrons are there per cubic centimeter. So that insulators are very scarce. They don't have electrons. So that cannot be used. This metals cannot be used, and even insulators cannot be used. But in case of semiconductors, if you see, in case of semiconductors, 10 to the power 8 to 10 to the power 19 per cubic centimeter of electrons are there. There it can be varied also, 10 to the power 8 to 10 to the power 19 by the process called doping. So that's why we go for this semiconductor. And in semiconductor, you have, say again, now we are going into semiconductor with P and N region. So if it is P plus or N plus, if you add more number of holes, it becomes P plus, and that should have 10 to the power 19 per cubic centimeter. If it is 10 to the power 19 electrons per cubic centimeter, it becomes N plus, and if it is 10 to the power 19 per cubic centimeter holes, then it becomes P plus. Okay. Similarly, if it is P minus and N minus, it is 10 to the power 14 per cubic centimeter, then we say it is P minus, or 10 to the power 14 per electrons, then we say it is N minus. So this is about the N minus and P minus region. And after that, we have the P and N. So P and N is, so P and N 10 to the power 19 per cubic centimeter. If the number of electrons are 10 to the power 19 per cubic centimeter, we say it is N electrons. And if there are 10 to the power 17 per cubic centimeter, then we say it is N region. And if there are 10 to the power 17 holes per cubic centimeter, we say it is P region. So that is in the general case of a diode. It is 10 to the power 17 per cubic centimeter, so it is a PN region. But what we did, by process of doping, we have changed it as P plus or N minus. That made the magic in order to withstand high voltage and high current. Okay. So next is, this is a power diode you can see here. So you can see that this is the basic symbol of a power diode. It has a P region and an N region, anode and cathode, and it is having here a, like, this is the general structure of a power diode. And you can see here these power diodes, mainly what we do, we screw them to the heat sink, because when these devices carry very high amount of current, automatically heat is generated there. So this heat may damage the device. So we usually, what we do, we screw them, or we just clamp them to the heat sinks. Okay, so that's why here you can see the screwing region, like a screw-like arrangement where you can screw this to the heat sink. And you can see here the structure, the schematic cross section of this whole diode is given here, which has a P plus region, N minus and N plus, where I already told you what is P plus, N minus and N plus. And now it is having anode, epitaxially grown layer, that is drift region is there. So this is the drift region. This N minus, this region is said to be the drift region. So the thickness of the drift region will tell you how much voltage it can withstand. Yeah, drift region is different. Depletion layer is, say, a depletion layer will be formed here in this, usually in this layer. Usually in a PN junction between P and N, a depletion layer will be formed here. And this depletion layer thickness will increase depending upon the bias what you have given. Okay, so this is a depletion layer. Depletion layer. So depletion layer has something to do with the doping. If this, say this is a depletion layer which I showed you, in case this N minus layer thickness is more, depletion layer thickness will also be more. It will go like deep into the N minus layer. Okay, if that's why in last case the depletion layer had a very thin thickness. Now what we are doing, actually we are increasing the depletion layer. So what happens to the depletion layer when there is an N minus layer? Automatically the thickness in the N layer will increase, and the depletion layer thickness in the N minus layer will increase, and it will like what you can say, it will penetrate into the N minus layer. So if the epitaxially grown drift region thickness is more, then the depletion layer thickness will be more. So as a result, you can have a large voltage drop. Like say large voltage is required to break down this diode. So that is the concept here. And this drift region in case of a diode, it will vary from 10 micrometer to around 200 micrometer. So if you keep 10 micrometer, the thickness is less, so low voltage, there will be a low voltage drop. Then you go on increasing 100, 200 micrometer, you can increase. So there a large diode with large breakdown voltage can be achieved. So this is the general layer. And as I already told you, the depletion layer is formed between these two things, and as you give a reverse voltage, and the other thing is here N minus layer is also there, so the depletion layer, a thick layer of depletion layer is formed here, and now you have to break this, so you have to give a larger voltage in order to break this region. Okay, so that is how this voltage in breaking down voltage, we are increasing it. And now at the same time we have to increase the current also. So for voltage, we told we can increase the depletion layer region by increasing the drift region. Next is, how will we make this device carry high current? So for making this device carry high current, what is required? A device is there, you want to make it carry high current. How is it possible? You have to, no, say electrons, anyway, large number of electrons should flow, but how it will flow in this device? You have to increase the diameter of the device. Is it? So once you increase the diameter of this device, automatically large number of electrons can flow through the device at a particular instant. Current. Voltage only I told you, the drift region thickness. When you increase the drift region thickness, the voltage, breakdown voltage will increase. Automatically the device will withstand so much voltage. Now the same device is there. Say you just take a pipe, water is flowing through it. So you want more water. Until you don't increase the diameter of the pipe, more water will not be able to flow in that. So that's the same thing, same concept here also. You have the device, and here a particular, say 1 amp is flowing. Now you want to make 10 amps flow through the device. One thing is the capability of the device. You have to see that the P region, N region, that should be capable of carrying all these electrons. The other thing is the thickness should also be increased. Yeah. So here same thing. So now this device will be able to carry more current as well as more thing. So different manufacturers go for different combination. It is not that it is fixed. So some say that there are different manufacturers like ABB manufacture it, Mitsubishi, Fiji, and UPEC. So there are different companies who manufacture all these power electronic devices, and they go for different thickness and different epitaxial thickness. So based on that, their voltage and current level also will be different. Basic? Yeah. There are basic standards also, but that's what I'm saying. I'll just show you a slide where different companies, how they are manufacturing different things. So the thing is, standard is this. P plus will be the electron density is fixed for P plus, N minus, and this. But there is you cannot go for a very large area also. There is limitation to that. And mostly if you see, say there are around 10 centimeter to 20 centimeter dia is generally used. Mostly in books, if you see 10 centimeter dia is given for for Thyristor for carrying some 200 amps or something like that. Okay, so they have some standards. Industry have some standards for fixing this dia as well as the thing. So that depends on what voltage they want to withstand also. So it not only depends on these two factors. The voltage also depends on one more thing. It depends on, say here I was just telling you P plus N plus. So N plus and N minus. In case if you make it as N and N minus, here you make it as N and N minus, that will also have a different voltage. There the voltage will drop faster. Okay, in there the voltage will be less, in the sense less voltage. Yeah, when it is N plus, there more electrons are there. Is it more electrons are there? So in that case, again the voltage withstanding capability will increase. You can have more volt, like, because N minus and N plus are the two extreme thing. Okay, N is near to N minus. So in that case, the voltage will drop faster compared to N minus and N plus. So here also you can have, in the first case, as I told you, instead of P plus, you can even have P. So different manufacturers, they come out with different combination. They keep a combination like P, N minus and N, or they can have P plus N and N minus and N. So you can go for different combinations. Yeah. N it is only, yeah, normal. So there is doping. So you have to decide how much you want to dope. You want to, how much electrons you want to add, how much holes you want to add. It depends there. Okay. So next is, commonly if you take the power semiconductor device, you can classify them into two. One is the uncontrolled and another one is the controlled. Okay. So here you can see in uncontrolled, you have rectifiers and accessories. Rectifiers in the sense the diodes. Diodes are usually diodes usually work as rectifiers. Accessories are in the sense, say the Triac, Zener diode, or the metal oxide varictors. All those things are used as the accessories for these uncontrolled rectifiers. Okay. So similarly, you can make them operate in controlled also. You can make the device controlled also. So for that controlled, if you see, you have three. Again, regenerative, non-regenerative, and integrated. So regenerative in the sense SCR, Triac and GTO comes under regenerative. And non-regenerative, that is BJT, MOSFET and IGBT. And integrated is PIC, intelligent power modules, and IGCT, like integrated gate, commutated thyristor. So these things comes under integrated. So what is regenerative and what is non-regenerative? In case of regenerative, say if you take an SCR or Triac or all these devices, once you fire them, they go into conduction. Once they go into conduction, then they, even if you remove the gate pulse, they remain in conduction. So that is said to be regenerative. They have a regenerative process action taking place. That is because each SCR is like two transistors connected back to back. That is called the Darlington pair. So when two transistors go into conduction, they go into a loop, and there. So once you give the gate pulse, it goes into conduction, both the transistors, and once you remove the gate pulse also, they remain in conduction. So that's why they are said to be regenerative. They have a regenerative. Non-regenerative in the sense, MOSFETs, IGBTs and BJTs, once you remove the bias, when you are removing the supply, automatically they get turned off. And nowadays, these circuits are not individual power, like power device you don't get. You get it as an integrated circuit. You get it as a intelligent power module. Okay, you get it as an intelligent power module. So if you want to get for a rectifier, already 6 rectifiers together with their firing circuit together, as a module you get it nowadays. Okay, so that's what we say, that comes in this integrated, where you have all the firing circuits as well as the device together, and it is an intelligent power module. So this is about this power semiconductor device classification. And as we all know, so BJT, MOSFET and IGBT, these are some of the devices, but in case of FACS, this is not much required, because FACS are operating at very high voltage and current level. Okay, FACS, it is in transmission and distribution. So here mostly BJT, MOSFET and IGBT are not used. In that cases, thyristors are used. Okay, that we will be seeing next, thyristors. But still, this power electronic device, this BJT, MOSFET and IGBT also plays a very important role in drives and other applications. So BJT, if you see, it is a current control device and it has medium switching frequency. So that is one of the disadvantage of this BJT. It's having a medium thing, and on-state voltage drop is low. So that is a very good property of BJT, which is not there in MOSFET. Okay, so now the new device is the cool MOS, which you can see. Cool MOS has all the advantages of the other three devices. Only one disadvantage of the cool MOS is it is low voltage and current rating. Still, you can see where you can replace this MOSFET, because 1 kV and 100 amps, till 100 amps, you can go for this cool MOS. That is one of the latest device which is used. And if you take the advantage of BJT, that is simple and low on-state voltage drop. That is the advantage. And the disadvantage is high switching losses. So whenever you want an application where high switching need to be done, you automatically go for MOSFETs and not BJTs, because here high switching losses are there. And coming to MOSFET, high switching frequency is there. It is a voltage control device, and on-state voltage drop is high, and its rating is a 1 kilovolt and 150 amps, and higher switching speed, like high switching frequency, high switching applications, you can go for it, and high on-state voltage drop. In BJT, it is low on-state voltage drop. Here it is high on. When it is, the device is on, there is a large voltage drop across it, so that is a loss there. Okay, so that's why MOSFET, that is a disadvantage of MOSFET. So these disadvantages of BJT and MOSFET was overcome in IGBT. That is also a voltage control device. It has high switching frequency, medium on-state voltage drop, and 3.5 kV to 2 like amps is 2 kiloamps. You can use this IGBT. Low on-state voltage and lower off-state voltage capability. So this is the advantage of IGBT, and the limitation is lower off-state voltage capability. And cool MOS, as I already told you, now these all other devices, if rating is not a matter, then we go for cool MOS. And now you can see here that which device to use for which application. You can just see this graph, and you can just conclude with this, that here below you can see 10 hertz or 1 kilohertz or 100 kilohertz. This is the frequency range, and this is the power range. In the y-axis, you can see the power range, and in the x-axis, you can see the frequency range. So based on the application, so you have a drive application where you want to operate the device at very high switching frequency, then you go for MOSFET. Because drives, not more than 10 kilowatt you go. For a drive application is not more than 10 kilowatt, so directly you can go for MOS. If you feel your drive is at more than 10 kilowatt, say in a generating station or somewhere, you want more than 10 kilowatt, then you can go for IGBT. 1 till 1 megawatt, you can go for IGBT. But the IGBT, the frequency is 100 kilohertz. It is limited to around 100 kilohertz, or you can say here around 10 kilohertz. That is the like fixed thing. Beyond that, it's slightly the graph, you can say it is drooping. So many applications, when the frequency is going high, the power level also will decrease. Around 100 kilohertz, if you see, you can use only around 3-4 kilowatts. So that limitation is there. So around 1 megawatts, in the sense around 3-4 kilohertz, you can use IGBTs. And we all know in transmission and distribution, the frequency is mostly 50 or 60 hertz. Okay, based on the countries, it is 50 or 60 hertz. So you can clearly see here, this thyristor, it is put it dotted, so it goes till 50 to 60 hertz. So thyristor is the only option for fax devices. Okay, so the fax, you mainly go for thyristors. Thyristors, you can just see in all the books also. That's why TCAC, that is thyristor based control only. TCR, that is also thyristor controlled reactor. So all these things are thyristor based devices, and thyristor is the main device used here. But what is the disadvantage using thyristor there? Thyristor is a unidirectional device. It makes current flow only in one direction. But we are using it for an application fax, that is a bidirectional, in the sense positive half cycle and you have a negative half cycle. When the reactive, yeah, you have to give the reactive power, like real power, it is you doing some useful work, and without reactive power, getting the back the energy to the source, that is through the negative portion, that reactive power is flowing. So if that is not there, then the device, like if it is unidirectional, then the source will not get energy in order to give it further. So real and reactive power both are required. So positive, like only one side, like it is thyristor is sending power in one direction. It has to get back the power. For that, as ma'am already told, you have to use anti-parallel thyristors. So when you use two thyristors in anti-parallel, first the current will flow in one direction and the next half cycle current is brought back. So these thyristors are mainly used for these fax devices. Okay. So, but at the same time, you know, we saw one more device, that is Triac. So Triac is a bidirectional device, is it? That is a single device where current can flow in both the directions. Then why we are not using Triac there instead of thyristors? That is best, I think. Yeah, it is related to the power level, because thyristors cannot be used for very high power applications, because now researches are going on to Triac. The manufacturing of Triac for such high level is very difficult. So that's the main disadvantage of Triac. Otherwise, Triac is very good. Both the sides you can, positive half cycle also you can control, and the negative half cycle also you can control. But the main disadvantage is manufacturing a device for high switching, like that is 50 hertz, not very high switching, also for 60 hertz switching, plus this high power level is difficult. Triac is for mostly, it is used for this household applications and industrial applications, in our fans and all. So I like, according to my knowledge, in fans 230 volts and some 5 or 6 amps is more than enough. But in industries also, for some of the applications in the motor. Yeah, research is going for fax devices. Very high power researches are going on. Till now also researches are going on, not Triac as such, a bidirectional device. A single device where, because here two devices are used. So again, two control circuits are required, firing this and firing this. So the circuit complexity increases. And it's a three-phase. Fax, you know, it is a three-phase. So you just imagine how many thyristors are required. So in that place, if two thyristors are replaced by one thyristor, the number of total thyristors can also be reduced. So that is a research going on to manufacture a device which is bidirectional. So it is a bidirectional device, Triac. Triac, the same device, okay, when like say you have fired, both the direction, like it can, you can control it in both the direction. I'll just show you Triac picture also I have beyond, where it is for low voltage rating. Say for example, I can just tell you, for an example of a motor, like say for our, let us take a ceiling fan itself. So in a ceiling fan, you have a switch. That switch is nothing but the Triac here. So let us have a so this is the Triac. Okay, this is the Triac, and let us assume that we have a motor here. It is a AC motor, but I'm simply just for a representation. Let me show. It's a motor here. It's a brushed motor here. Okay. So now what will happen? Now you're giving AC supply. You're giving an AC supply to this motor. Okay. It will run at full speed. Now you want to control the speed of this motor. If you put here a resistor, what will happen? You can reduce this voltage. AC voltage, positive and negative, you can do it. But what will happen? That power will drop there. Say we are giving 230 volts to this motor. Around 100 volts, you are dropping it here, and the remaining 130, you are giving it to the motor, so it runs at a particular speed. So this 100 volt, what is happening? It is dissipated at heat here. There is a power loss there. So in case of Triac, what you can do is, during positive half cycle, at this point you're firing, so you get this portion. See, this portion, you get it for positive half cycle. Similarly, the negative half cycle, you can get this portion, the blue portion. It's not so clearly I drew, but still this positive, and here, so this portion, the portion in green which I am showing is clipped off. We are not taking it from the supply itself. We are turning, this is just, see, all these power electronic device, you can just imagine them as just a switch. This is a switch here. So when you are turning on the Triac here during the positive half cycle, this blue portion will come to the motor. Okay, similarly, here also you are not turning it on. When it goes reverse, at this, say around here 30 degrees you're turning, then 180 plus 30, at this point again you're turning. So this negative half cycle blue portion will come to the motor. So the average, if you see, that average will be some value like this. The average AC will be a value like this, which is a lesser voltage compared to the original voltage coming. So this is the power Triac, what it is doing. It is just clipping some portion. Okay, you're just firing the device. So all these devices, if it is a Triac or a Thyristor or all these devices, it acts like just like a switch. So what is the difference between the ordinary switch what we use here and this power switch? So here also say you just have a 555 timer or some timer and you can control it. Is it? You have some calling bells or something where you can have after some time, you can have some control attached to this switch also. Then why we are not using? Or you have gone to this manufacturer, you would have seen, they just test it. They have a control circuit and they do it like per second at very high speed. They'll be switching an ordinary manual switch here for testing purpose. So, yeah, they very high speed. They just turn on just to see the durability, how much time it can be turned on per second and all. So that in the sense that switch can also be with some control circuit. You can turn on and turn off. Then why do we go for all these switches? Fast switching might be. That also you can do, not very high switching, but switching is possible there also. There circuit also in machines lab and all, we used to have double pole, double throw switch and all automatic switchings. All these things are there. But the main advantage of this power electronic switches, they are static switches, we say. They don't produce any arc or any flash over. Usually these switches, there will be a small arc formed and there is some loss there. But these power electronic switches, we are just forward biasing them or reverse biasing in order to. Which one? Power electronics? Triac. Yes. Okay, you're telling about Triac also here only. We are using nowadays the fans which we come, you have small regulators, you know, they are Triac based. That is also 230 volts. Okay, even 440 volts you can use Triac. Then I don't know higher than that Triac how much it is going. All power electronic device, you have devices which can be operated. I'm saying it can have some 10 kilowatts and 2000 amps it can carry, 2000 or 5000 amps. Then these switches and the static switch, the general difference is these switches are manual switches. Okay, mainly you can say, but they can also be controlled. That is the other part. But main thing is when they are turned on or turned off, there's some arc is produced there. Some firing, like small arc will be produced. That is, in some case, it is dangerous. Okay. So these devices, these power electronic devices, which we saw, they can also be operated at very high voltage, but they are just forward bias or reverse bias. So they are said to be static switch. Nobody knows when it is getting turned or off until you see the characteristics. You can control it according to your requirement. So this is the power electronics. So mostly, as I already told you, thyristors are used for this application. Until now, we saw all the switches. Using these switches, next we will make some circuits. Okay, these switches are there. You can make some circuits. That you will be seeing next. So here, some of the applications are again shown. You have the fax devices, HVDC. So the rating, voltage rating and current rating are also given here, the power rating. And similarly, device which are used. So for power around 45 kilowatt and megawatt and above, you can see SCRs are used. So for our application, what we are discussing in this course, mostly it is SCR based. Okay, so as I already told you, many of the companies like Mitsubishi, EPEC, UPEC, ABB, Fiji, all these companies are manufacturing these thyristors and MOSFETs, like all these power electronic devices. And you can see their ratings also. So you can see here, Mitsubishi's thyristor, it is around 12 kV and 2360 amps. Okay, and the same thing UPEC, you can see one more thyristor here. The current rating is more. In this case, you can see 660 amps, but the voltage rating is 8,000 volts. So all these companies, they manufacture, as I already told you, based on the P plus N minus layer and the thickness of the epitaxial layer, and all these things decides what is the voltage and current rating. And based on the application, okay, they just choose, say a company is giving an order like we want to for so and so application, and this is the rating, accordingly they manufacture it. Okay. So you can see here, these are the different devices which are manufactured by different companies. So a GTO by Mitsubishi, it is around 6,000 volt and 3,100 amp. And this shows a table of characteristics and symbols of power electronic device. So here you can see the diode, its characteristics, thyristor characteristics, and you are a static induction thyristor, GTO is there. Then you have MCT, MTO, that is MOS turn off thyristors, and ETO, emitter turn off thyristors. So these are some of the thyristors. And similarly, you have IGCT, integrated gate commutation thyristor, and you have Triac. Triac, what I already told you, it is a bidirectional device. It can be controlled both the first and the third quadrant. You can see the characteristics. Then you have a light activated SCR, okay, and PNP, BJT, IGBTs, and N channel MOSFET, and SIT, static induction transistor. So these are the different devices, switches, which are power devices which are available. And using these switches, we make different circuits. That is what I said. First one is a DC to AC converter. So what is a DC to AC converter? In our houses also you would have used inverter. So inverter, you have seen batteries in your houses. And this battery, when power supply goes, what will happen? This battery is supplying to all your AC load. So that is nothing but DC to AC conversion is nothing but an inverter. Okay, so AC to DC conversion, that is inverter. So these inverters, at what are the other places you use? One is at your home. Okay, you have then in your computers, SMPs and all, you are having online and offline inverters are there. In that SMPs also you have a battery and you give power supply, AC supply, you convert it. Then mainly in say fax, you don't go for much DC to AC conversion. But in case of DGs, distributed generation. So distributed generation, most of the distributed generation, if you see, they are DC. Okay, solar, mainly solar. But wind, if you see, that is AC. But that wind also, what you do, second step, that AC you convert into DC. Because we required AC, like a dedicated AC at the output. Okay, a controlled AC at the output. So for that case, even in wind, you convert AC to DC, then you convert DC to DC, and then again DC to AC. That is what is done in wind. So first of all, we'll come step by step. So DC to AC conversion, a simple example you can take of a solar PV. In solar PV, you have a PV array, and that PV array output is DC, that is known. That DC, you will again convert into required DC. So DC to DC converter, that is a chopper, you can say. You will be using that as the next topic here, that is DC to DC conversion. You use a chopper, DC to DC converter. And this DC, now it is a controlled DC. You know what is the DC required. Okay, that DC can again be converted into AC before giving it to the grid. Okay, your grid is AC. Your solar is giving DC. So that DC which you're getting from solar cannot be connected to the grid directly. Because the solar is, the irradiation is not uniform. Okay, the uniform, that every time it goes on changing. So what you can do, usually you can have a battery. You can have a battery, and battery can be charged from the solar, so that the battery will give you a fixed voltage always. Okay, that is the thing. So battery, how will you charge? The solar voltage which is coming from the irradiation, say irradiation on a particular temperature, that is 1000 watts per meter squared, and 25 degrees C is a common standard test condition for a PV to give maximum efficiency. Now the irradiation is less, think 100 watts per meter squared, and the temperature is also say 24. So you get a particular voltage. You have to get maximum, say open circuit voltage is 21. But when the irradiation is less, you don't get that. You get only 10 volts. Now this battery has to be charged. Okay, the battery has to be charged. With this 10 volts, how the battery will get charged? So what is required there? You in between, you put a DC to DC conversion, where the DC has to be converted to again DC, required DC. Okay, so that DC to DC converter is nothing but a chopper. So there, say you can have a buck boost converter. Buck boost in the sense, it will either buck the voltage, reduce the voltage required, or it will either step up the voltage. For example, say you have a PV, and now the voltage which is coming, you have maximum irradiation during the noon time, and the voltage coming is 21 volts. So what happens? The battery is only 12 volts. So in that case, you have to reduce the voltage. Okay, is it clear? So you use a buck boost converter. Okay, or a step up step. Huh? It is not a saving device. It is never a saving device. It is just a converting device. it will just convert one form of energy to another and give. So here it is converting DC to DC. Okay, it is not saving. So saving is like battery is a bank which is storing the energy, you can say. Magnitude, it is just changing the magnitude. Say PV voltage is coming, it is some 21 volts I said. So this battery has to be charged there. 12 volts is required. So this is just like say for AC you take a transformer. What a transformer does? It is either steps up or steps down the voltage. Okay, same thing it is doing here. This DC to DC converter also, when 21 volts come, our requirement is only 12. So what it will do? It will reduce the voltage. By changing the duty cycle of the MOSFET, there you can reduce the voltage and charge your battery. And now in case the voltage is very less, only 10 volts, you want to increase the voltage. Automatically what will you do? You will change the duty cycle of the MOSFET. The voltage will be increased. So say 10 volts is there. If the duty cycle is if you want to boost it to 20 volts, then you will be just multiplying there. The sense say there in case of a buck converter, the output voltage is nothing but duty cycle times the input voltage. Duty cycle times the input voltage. Okay, so you want to buck it, you want to reduce it. So I can just show you the equation once again. So the output voltage is nothing but duty cycle times the input voltage. So say your input voltage is 10 and you want to you want your output to be 5 volts. Your output should be 5 volts. So what will be your duty cycle here? 50%, that is 0.5. It's 50.5 now. So it will get you, if you have 0.5 here, what will happen? It is 1/2, so you will get output 5 volts. So that is how. So by changing the duty cycle of the power device there, automatically what is required, you can achieve it. In case of boost, So in case of boost, the circuit is little different. You have an inductor also. Okay, in the boost case, at the input end, you have an inductor. So first what you do, you just turn on the switch and inductor will get charged there. Inductor will start storing the energy. Second half, when you remove it, source plus that inductor will give you the double there. Okay, so that is in case of boost. Anyway, I have not drawn the circuit here, but initially there, the switch will be in the middle, like it will be parallel to the source and the load, and there will be an inductor in series with the source. So when you turn on the switch, the inductor will get charged, and when you then that inductor is fully charged. So when the inductor voltage is equal to the source voltage, okay, now the switch can be put on the other end. So this whole voltage, that is a double voltage, will come across the load. That's a very good question, because every time we will get confused, only source is 10 volts, how it is becoming 20. So some energy storage devices required in between. Yeah, but actually there again you have to see, capacitor will act like once it is on, it acts like a short initially. Okay, then it takes time to charge. And the other thing is, once it is fully open, it acts like a volt, it becomes open, but still it becomes open there. It becomes, at the final stage, it becomes an open there. Circuit should not be open. Both the sources should be connected in series. So this acts like a current source. Inductor will act like a current source there. So when the capacitor is fully charged, it becomes an open there. You will get a voltage, but it is open. Circuit will be open circuit there. Time constant. The time constant is also there. But both the storage device can be used, but its placement has to be seen. Okay, you can use both, but usually generally the boost converter, if you see, they use an inductor there in the circuit. They say that the inductor fully stores the energy, and like at the end. So here, this is the general theory of it. And again, you can see here, DC to DC converter, choppers are used. DC to AC inverters are used, and AC, sorry, it is not used, it is the name given. And AC to DC, it is rectifier. And AC to AC, there are two types. One is cycloconverter and another one is the AC voltage controller. So here AC to AC, cycloconverter, in the sense it converts AC to AC. Whenever you want to step up or step down the AC frequency. So whenever you want to change the frequency of the device, then you go for cycloconverter. AC voltage controller is where it will step up or step down the voltage. there are two types of AC to AC, similar to that of a transformer. So AC to voltage converter is similar to that of a transformer, but cycloconverter, it will change the frequency also. So this is a thyristor circuit you can see here. It has a PN structure and the anode, gate and cathode. So a general structure is also shown. So this is the vertical cross section of an SCR. So here you can see that N plus layer, that is 10 to the power 19 per cubic centimeter, which is the cathode at the top. The gate is the P region here, 10 to the power 17 per cubic centimeter. And N minus region is there, which is between 10 to the power 13 to 10 to the power 14 per cubic centimeter, and whose thickness can be varied from 50 to 1000 micrometer. So thickness of this depends on the what is the voltage it can withstand. It has a P and a P plus region also. So that's what I said. You can have different. This is totally a P region, but this manufacturer has divided that into two regions, and they have given a P as well as a P plus in order to achieve a particular voltage level. So you can. This is the overall structure. Okay, and this is the general cross-sectional structure, and this SCR, it can be, that is a thyristor, can also be represented as two transistors in Darlington pair. So we are going to the characteristics of a thyristor. So we have to know how the device operates. So initially in the forward bias region, like when it is for the thyristor is forward bias, you all know thyristor, I told you once a gate pulse is given, then only it will turn on. So once it is forward bias, some minority carriers flow in that. So because of that, here you can see this small current. This is the small current that is existing even when it is forward bias. So small current flows through the device. And say now the current is less, like it is only so much. When the gate current flowing is, sorry, when the anode current, you can say it's the anode current there, due to the minority carriers, when it is very less, and the applied voltage is also less. This is the anode cathode voltage. You are applying only less voltage. Now you have to give more gate pulse in order to turn it on. Okay, minority carriers, say it is flowing through the circuit thing. Now the forward voltage, what you have given? You have given a forward voltage. Say you have given 10 volts as forward voltage. So in that case, you have to give more gate pulse in order to turn it on. At the same time, when you give 20 volts, the gate current which is required is only, the magnitude of the gate current required is only less. So that is what you can see. IG4 is the gating pulse here in order to turn on the thyristor, but that is greater than this IG3. As you go this side, your gate current required is less. And at this point, what happens? Breakdown. So even without gate current, that is gate current is equal to 0, it gets turned on. So every device has a forward breakover voltage given. That will be given in the data sheet. You have to just see that. If we give a forward voltage more than that, say the device has to be operated 230 volts. Now we are giving 240. Automatically the device will break down and it will go into conduction or sometimes burn out if it is a very large amount, large value. Okay. And here you can say once you give the gate pulse, it goes into conduction, and this is the characteristics you can see here. So at that time, you can see here a small voltage drop. It is around 1 to 2 volts voltage drop is here. Okay, so this is the small voltage drop which you can see here in the device when it is in conduction. So this voltage drop should be a very small value. If it is a larger value, that is a loss there. Okay, so that is also a major concern you have to take into account. And when you're turning it off, you have to just take care that the current, that is the anode current, should go below the holding current. So that is a minimum current which is defined, below which the anode current should be taken in order to turn off the device. Similarly, there is something called latching current. So latching current is a current above which this anode current should go in order to make it to conduction. Okay, so this is latching current and holding current. So whenever you want to turn off the device, you have to make sure that the current has gone below the holding current. Otherwise, again, it may go into conduction. So this is the thing. So this is the reverse bias characteristics. So you can see here in reverse bias also, there is a small voltage drop across this device. Okay, so this amount of reverse, like due to the minority carries, there is some, sorry, not voltage drop, there is a small current flowing through it. And here this is said to be the avalanche breakdown. If you go on increasing the voltage in the reverse direction also, one particular point, the voltage will drop. And in this case, this is a practical case, so they have shown it directly going straight like this. in the sense the maximum current is flowing. But generally, if you see, this characteristics will be drooping towards inside, because the circuit will also have some resistance, is it? So because of that resistance, what we can observe is it will not straightly increase, it will not go to infinite, it will just droop inwards like this. So this is the general characteristics of a thyristor. Okay, so next is the gate characteristics of a thyristor. So every device, if you take, you require a gate circuit there. So generally nowadays we don't go for this RC firing, UJT firing and all. Nowadays, if it is digital firing, because they are more, to say, whenever you want to change the circuit or do some improvement in it, or you want to have high reliability and fast switching and all, nowadays digital firing is done. So in digital firing also, the gate circuit, if you see, you will have the optocouplers for isolation purpose. You will again, you will have the driver IC in order to drive that, because the supply which you are giving the gate pulse, it will be like, say, my microcontroller is there, it will give you only 5 volts. Sometimes the thyristor which is requires a firing of 12 volts. So in that case, or 9 volts. Some thyristors require 9 volts, some require 12 volts. So this microcontroller or some other controller device, the 5 volts is not enough to drive this thyristor. So another thing is, this circuit where the thyristor is connected is said to be a power circuit. Is it? That may be a thyristor with a motor control, or it may be a fax device. So that is operating at very high voltage and current. As I already told you, 5000 amps is flowing, or it may be a voltage like 10 kV or 5000 amps there. And or a drive application, 440 volts, 3-phase supply with some 15 amps. So the microcontroller, it is at a very low level, 5 amps and few milliamps. So what will happen, this high power, always current flows from higher potential to lower potential. So this high current, if it flows into your device, what will happen? Your microcontroller will get burned off, or you're connecting an FPGA or something, it will get burned off. So every time you require something called isolation in between. One is, you can achieve this isolation using optocouplers, or you can use pulse transformers. In power electronics, you get something called 1:1:1 power pulse transformer. So this pulse transformer 1:1:1 can fire 2 thyristors at a time. One, you will be connecting it to the control circuit, and 2 1:1:1. So 2 output can be taken and it can be given to the circuit. That is pulse transformers. Or you can use optocouplers. Optocouplers also, you will have optocouplers. I'll be showing you a circuit of dual converter where we have optocouplers. So these optocouplers also give an isolation between the power circuit and the control circuit. So isolation is there. Next stage is you have to drive it. That thyristor will not get turned on if it doesn't get 12 volts. So what you you will take a driver IC, and this driver IC will be given at 12 volts. And when this optocoupler detects a signal there, automatically that 12 volts will go to the thyristor, and the thyristor will get turned on. So this isolation is mainly required. So now whenever you choose a gate circuit, so now you can see in the PPT that the gate characteristics is given here. And this gate characteristics, you can see here, one is the minimum characteristics and another one is the maximum characteristics. So this is the maximum characteristics you can see here. So any thyristor, when you take, the characteristics of your circuit should not be more than this. If it is more than this, your circuit will get burned off. Thyristor characteristic not be more than this, and similarly it should not be less than this also. If it is less than this, then your circuit will not get turned on also. Okay, so this is the characteristic, and here they have given, this is the VG max, that is the maximum voltage that can be given to the gate circuit can withstand. Similarly, the maximum current rating is also given here. Similarly, they have given a minimum value also here. You can see the voltage and current. That is a minimum value which is required to turn on the gate. Okay, and the minimum current which is required. If that minimum value is also not given, then the thyristor will not get turned on. One more value is given, that is VGN. So this VGN is nothing but, say there is some electromagnetic interference in the circuit, or all these power circuits I have told you nowadays, it comes as a module. Okay, it comes as a single module. So there will be 6 thyristors in that, and one thyristor is turning on. What will happen? It creates some electromagnetic interference, or like some vibration or something is there that may affect the other thyristor, and by automatically the other thyristor may also get turned on. Due to the turning off one thyristor, the other may also get turned on. So mainly due to some electromagnetic interference nearby. So they have given one more limit, that always our gate circuit, we have to keep in mind that our gate will not get fault triggered. By mistake, it should not get triggered. That is also a problem. So they have given a minimum value, and they have said ki when the voltage is below this, then it is false triggering. You need not take that voltage. So you will be fixing a voltage at when the voltage goes above a particular, that is VG minimum, then only your circuit will get turned on. So now when you choose a characteristics, your characteristic should be between these two characteristics. Okay, so in this case, if you see your load characteristics you are plotting. So the whole circuit you take the open circuit voltage, that will be this point. You take the short circuit current, that will be this point. Join these 2 points and your curve, and this will be your operating point of your circuit. This point your device will operate. And you have to see that this point should be more close to this P gate average value for an efficient thing. So in the sense, your load characteristics should be almost parallel to this PG average. The load characteristics which you plot should be almost like tangential to this PG average. That is the best characteristics of it. So in that case, you can see the load, your operating point will be this. Okay, so you have to choose, like when we choose these devices, the gate devices also, you have to be very careful. You will be just choosing what is your VG, what is your IG. You have to test the gate circuit first, then you will be connecting it. This is the gate characteristics. Next, we go to the switching characteristics. I'll show a single circuit. So this is the switching characteristics. So in switching also, there are 2 regions. One is the on state and another one is for off. Okay, so here T on, in this case, you can see it is divided into 3 regions. One is the delay time, one is rise time, and one is the spread time. So 3 regions. So delay time is nothing but the time taken for the anode current to rise from the initial, like the minority carriage which was flowing, to 0.1 of the final value. So this is the delay time. This region is the delay time. What is rise time? Rise time is the time taken for the anode current to rise from this 0.1 IA to the final to 0.9 IA. So that is the rise time. And the spread time, it is the time taken for the anode current to rise from 0.9 IA to the final value. Same way in terms of voltage also we can define this. So this overall together is nothing but your turn on. But in turn on, you have to just remember, during this rise time, you can see there is more power loss. Okay, so this we cannot do anything. The rise time, that depends on the manufacturer, but you can see in the data sheet and see whether the rise time is more or not, and accordingly you can choose a device. So when the rise time is less, it is better, there will be less power loss. And the other thing is, say there is a process called, once the device goes into conduction, you want to turn it off. 2 types. One is natural commutation. You have an AC supply, automatically it will get commutated. Otherwise, forcefully you have to commutate. How will we forcefully do it? Forcefully, when you want to do it, you connect a capacitor, make it fully charged, and make it reverse to the thyristor. When it comes reverse, automatically it will reverse bias the thyristor, and thyristor will get turned off. So that process is called commutation. We will be seeing some methods. I think we are going out of time, so I have to just rush. So here, once you commutated it, what will happen? Your current will start falling. And here you can see this recovery time, reverse recovery time. This is the gate recovery time, TGR, and the whole thing is the turn off time. And the circuit turn off time is TC given here. So the whole thing you can see here. So around this, from T1 to T2, around 66% of the whole electrons are flushed out. Say when the thyristor is conducting, the electrons are flowing through it. Suddenly you have given a reverse bias, you're turning it off. So it will not get turned off at that instant itself, because all these electrons which were there inside has to be flushed out. So from T1 to T2, when you are given a reverse bias, and from T1 to T2, what will happen? Around 66% of the thyristors are flushed out. After that, T2 to T3, during that time, at a faster rate, they are flushed out at a faster rate. That rate of change that you can see here, it drops at a higher rate. So what happens when it is flushed out at a higher rate? The voltage, there is a dip in voltage here, a negative voltage, high negative voltage is applied here. Okay, so this negative voltage also depends on the inductor present in the circuit. If the inductance value is more, then this voltage drop will also be more. That may damage our device. So we have to take care what is the inductor value connected in our gate circuit. Okay, why do we connect this inductor? That is di by dt protection. When there is a sudden rate of change of current also, your device will get damaged. So not to limit that, you put an inductor there which will limit the flow of current. So because of that inductor, when we are turning it on, there will be a negative voltage that may damage your device. Next is gate recovery. In the gate region also, some of the electrons will be like locked there. So these electrons should also be flushed out. That is done by this. So that is done during this T3 to T4. So that is the gate recovery. And at the end, you can see the TC, circuit recovery. Because this is a gate circuit. Another thing is the whole circuit. You just take the load and all what you have connected. So in that load, if there is some inductor, the circuit will not get turned off. It depends on the load also. So that whole circuit is get turned off during this T5. So this is the overall characteristics of the thyristor. I went into thyristor because thyristor is usually used in fax and mostly in DG applications. In DG applications, even MOSFETs and IGBTs are used because DC to DC converter at PV, you will use those devices also. Okay. So next is thyristor firing techniques. So I'm not going into depth because we are going out of, I have to explain you in the concept of voltage source converters also. So triggering techniques, you have different triggering techniques. One is the forward voltage triggering. When you increase the forward, that is a breakover voltage also we saw. When you go on increasing the voltage at one instant, your thyristor will get turned on. Another one is dV by dt triggering. When there is a sudden rate of change of voltage, again, this thyristor will get turned on. So here there is a concept of capacitor. You can take a capacitor's charge into C dV by dt, and you can explain this. Whenever there is a sudden change in voltage, the capacitor charging current will also increase to a large amount. Okay, because IC is proportional to dV by dt. So this thyristor is just like a capacitor there, and it may when there is a sudden change in voltage, this charging current also will increase. So because of that, also triggering can occur. But these two methods are not preferred. There is temperature triggering. You can increase the temperature of the junction automatically, gate junction, and it can be fired. But this is also not preferred. Then another one is light triggering. So you can use some optical fibers, make a light fall on a particular gate terminal. So automatically that can be fired. And gate triggering. So gate triggering is a common method which is used. Other methods can also be used, but mostly we don't prefer it because they have number of disadvantages. This light triggering can be combined with gate triggering also. So with light, to some extent, you can make a voltage drop using this light, and after that a gate. So combination is also possible. Temperature with gate. You are increasing the temperature, and after one particular temperature is reached, suddenly gate pulse can be. So combination is also possible. So this is the light activated thyristor. You can see here the optical fiber, and from this center point, it goes into this gate circuit. Okay, so sorry, the gate terminal. This is a gate, and this gate triggering, this is all the conventional analog values, so we are not going into it. Nowadays it is mostly digital based. So you have resistance, there is resistance in RC, R firing and RC firing, UJT firing, and pulse transformer in firing circuit. So here you can see when the voltage across this resistor, where you have to vary this resistor, and when the voltage across this 1 kilo ohm becomes the voltage of this firing of SCR, automatically this SCR will be fired. Similarly, you have a capacitor RC based firing is also available. UJT firing, so this UJT firing, the intrinsic constant, that is eta, is nothing but RB1 divided by RB1 plus RB2. Okay, this is the intrinsic constant. So usually if you see this P region, it is heavily doped P region, and you have an N region here, and this N region, it can be represented as two resistors, RB1 and RB2. So that is what is shown here, and this is the intrinsic constant. Okay, so in the UJT characteristics, this negative region, this slope, you can see this is used for firing the SCR. So that we will show how. So here, this is your UJT, and this is your UJT, and this is the thyristor. Okay, here they have used a pulse transformer for isolation, not to fire this. So you can see here the characteristics of an SCR. This is the negative region. Okay, again positive, and this is the negative region. So during this negative region, you clamp the voltage here. That is what is done here using a thing. So you get a spike there. So this is the firing pulse which you can give it to a thyristor. But at what frequency this should repeat? What is the frequency at which you want? That is, it depends on what is the firing angle, or what is the firing angle and what is the firing period when you want to repeat it. That firing pulse frequency, it depends on 1 divided by RC ln 1 divided by 1 minus eta, where eta is the intrinsic constant which I told you before. RC is the time constant. Here you can see this R and C value. So from that you get the time constant RC. 1 divided by RC ln 1 divided by 1 minus eta. Okay. So this is the pulse transformer based firing that is used for giving isolation to the circuit. And these are some of the devices you can see here. You can see PUT, SUS, SES, these UJT, all these are used for firing purpose. Okay, SBS, STS, DIACs, ATS, all these things. Next is thyristor protection. That is also very important. So in thyristor protection, you have something called snubber circuit, over voltage protection, current protection, and gate protection. Okay, so you use heat sink for removing the heat, like for dissipating the heat, you can say. So there are different structures available, and you can see the device also clamped to it. Okay. Snubber circuit. So this is almost available in all the devices. Nowadays, as a module, when you get a thyristor, mostly it is inbuilt available. So this snubber circuit is just used for dV by dt protection. So you can see here a capacitor and a resistor is required, which is in parallel with the thyristor. So initially, if you see, just imagine that there is no resistor. Okay, I'm just shorting it. There is no resistor. Only the capacitor is required for this purpose. So when, say, let us assume that you are giving here some 230 volts. So what will happen? When you initially turn on the supply, this is DC supply, so capacitor will act like a short. Okay, initially the capacitor will act like a short. So when it is shorted, what will happen? What will be the voltage across the SCR? It will be 0 volts. Initially, when you give DC, the capacitor will act like a short and the voltage across the thyristor is 0. Okay, now what happens? The capacitor will start charging. So when the capacitor starts charging, it starts charging, automatically what will happen? Say it is charging in this direction, plus and minus, like it is getting charged here. So the voltage will start developing across the thyristor from 0 gradually. Because the capacitor is charging, similarly the thyristor voltage also from 0, then 10, 20, 100, then at last it becomes 230 volts. So when it is around 230 volts, now the thyristor is forward bias. In the sense, now it is forward bias, ready to get fired. At any time you can fire, the thyristor will get. So now, when you fire this thyristor, what will happen? Current will start flowing through this. Current will start flowing through this. At the same time, the capacitor, this also forms a closed circuit. The capacitor will start discharging through this. So high current will come and damage your device. So in order to limit that, we have to see the whole circuit. We have to just write the equation KVL, KCL and KVL, and accordingly see that what should be the resistance value so that the current flowing through this is reasonable, like limited within the rating of the device. So that's why we put here a resistor. Okay, otherwise the resistor is not required, but when it is, because the current is reversing, automatically large current may damage your device, so they put a resistor here. So this RC combination is nothing but your snubber circuit. Apart from that, you have an inductor here. This, as I already told you, it is for your di by dt protection. So di by dt protection is given by this inductor, and I already told you this inductor is that which is causing a negative voltage during the turning off process, and you have to take care of this value also. Okay, and this crowbar protection, the crowbar protection, this whole circuit, power converter is protected by a thyristor here. So you can see here the large current, where current will flow like this until this thyristor is not turned on. So what will happen when large current flow through this thyristor, this resistor, automatically the gate circuit will get activated and turns on this thyristor. When this turns on the thyristor, this becomes a short here. So when it is short, all the current will get bypassed like this. So this is crowbar protection. This circuit is protected. Okay. And you have the gate protection. So all these protections together, it is shown here. You have overcurrent protection. There is circuit breakers and fast acting fuse is there. Di by dt protection is there. You have the snubber circuit. You have the heat sink. This is the gate protection. So in gate protection, if you see, this portion is the low pass filter. This is the low pass filter, okay, and then this is for limiting the current. This resistor R2 is for limiting the large current flowing through this circuit, and this Zener diode is for clamping the large voltage coming. So this is for current protection, this is for voltage protection of the gate, and this is low pass filter in order to eliminate the lower harmonics, and one more thing is done here in this gate circuit. You can see here, like it is not shown as such. Here the coils also will be coaxial, like it will be turned so that the electromagnetic interference from the nearby circuit can also be eliminated. So when the gate coil is there, the gate circuit, the gate wire, what you're saying, that will also be twisted, so that gate protection is also done. So this is the gate protection overall. Okay, commutation, as I already told you, there are different types of commutation. Process of turning off a conductor, like process of turning off a conducting thyristor is said to be commutation. There are two types. One is natural commutation and another one is forced commutation. Natural, as you all know, when it is an AC supply given, automatically when the AC crosses the zero, the thyristor will get turned off. Turn off here. At this point, the thyristor will be turned off. And next is the forced commutation. So natural commutation, whenever AC supply is used, say AC to DC conversion, a rectifier, okay, AC to AC conversion, like a cycloconverter or AC voltage converter, there also AC is there. Okay, in such circuits, you directly go for natural commutation. But in AC to AC also, say if it is a step up cycloconverter, in one cycle itself you want to turn off many times, then you have to go for forced commutation. So forced commutation also two types, current commutated and voltage commutation is there. And forced commutation is mainly used where your input is DC. Say DC to DC converter, forced commutation is used. DC to AC conversion, that is inverter, choppers, all these places you go for forced commutation. So natural commutation is used in AC voltage controller, phase control rectifiers and cycloconverters. And forced commutation, that is applied to DC circuits, and mainly your capacitor will be there, you will be charging it, and reversely you will be applying. Commutation achieved by reverse biasing the SCR by reducing the SCR current below the holding current. And commutation elements such as inductors or capacitors are used for commutation purpose. And method of forced commutation, that is forced commutation is self commutation or the load commutation. So you use a load which is resonating load. So when it is resonating, automatically the voltage or the current will zero cross. So automatically you can turn it on. Resonant pulse commutation, that is you use an inductor and you send the current, resonating circuit will be formed, and that inductor will send a current against this thyristor and you can turn it on. Complementary thyristor. One thyristor can be used for turning on the other thyristor. So that is complementary. And impulse commutation. Impulse commutation is nothing but the voltage commutation. By using a capacitor, you charge it to the maximum and give a reverse voltage, that is impulse commutation. External pulse commutation. Externally also, you can use a circuit in order to commutate it. So this portion I'm just skipping because we are going out of time. These are the different commutations. Then Triac, as I already told you, so it is similar to two thyristors connected anti-parallel. Okay, so this is it can be operated in all the four quadrants, and this is the characteristics of thyristor. And as I already told you, it can be controlled in both the like positive half cycle and negative half cycle can be controlled. So now we are just mainly going into the three-phase full control bridge converter. Okay, and circuit diagram it's shown here. So three-phase full bridge. So mostly in fax devices, if you see the UPFC or SSSC, all these things, they use voltage source converters. So voltage source converters are just like rectifiers here. You can see here that they can be either acted as a rectifier or an inverter. Okay, so that is the thing. Like the simple bridge circuit is same. By changing the firing across the thyristor, you can either make them operate as a rectifier or you can either operate them as an inverter. Okay, so here rectifier in the sense you have an AC supply, you are giving supply to the load. And when the load is capable of giving supply back to the source, then there is an inversion occurring. The load is giving supply to the source there. So by changing the firing angle, you can achieve this. So first of all, you can see, I'm just taking a simple circuit and I'll just explain. You can see here, I'll just show you the circuit. When I minimize, you'll not be able to see it clear. So here, this is T1, T3, T5, T4, T6 and T2. Okay, so whenever if it's a three-phase supply, you have to just remember based on the number of phases, you just define this. So always the odd one at the top, 1, 3, and 5. Okay, I put the odd one. Now it is a three-phase supply. So when it is a three-phase supply, 1 plus 3. So that gives you T4. Then 3 plus 3, that gives T6. And 5 plus 3, it is 8. But 8 is not there. So minus again 6, you get this T2. So this is how you just define which are the thyristors. Okay. And the thyristor, why we have named like this? When thyristor 1 is turned on, say T1. After that, after 60 degrees, your thyristor T2 will get turned on. After that 60 degrees, T3 will turn on. So it will be turned on in this order. First this thyristor, after 60 degrees T2, after 60 degrees T3, then this thyristor will get turned on, and T5 after T4, and last this T6. So that is how you name it also. So this is where, so I think you will know the numbering. And next, the three-phase supply, all of you know the three-phase supply here, which is drawn here. I'm just naming it. So first of all, say from 0, the voltage is rising and going down. So let me name this as VAB. So this is VAB. And you all know that you have three-phase. It is A, B, and C. You have A, B, and C. So A, B, and C. So this is VAB. Okay, and this is nothing but your VCB. Okay, and you know that each phase is more positive. In case of a three-phase supply, each phase is more positive for 120 degrees. Is it? When A phase is there, 120. After 120 degrees, what will happen? B phase will become more positive. After 120 degrees, C phase will become more positive. So here you can see the first one, initial one, what we saw is VAB, and this VAB, and the first circuit which was around, say, which was decreasing, the voltage which was decreasing, line voltage which was decreasing, was VCB. So here you can see the C phase was positive for 60 degrees. Okay, and after that, A phase became positive, and during the negative, like here you see B is negative for 120 degrees. B is negative for 120 degrees. BCB hai, yahan AC hai. After this, what will be the next thing? It will be VAC. Okay, because आपका ये तो 60 degrees के लिए positive रह गया, और वो मैंने बोला कि each phase will be positive for 120 degrees. So here A was positive for 60, again one more 60, it will be positive, more positive, so VA. Okay, and here you see B was negative for 120 degrees, and here C became negative, so C will continue for again 120, is it? So this one will be VBC. So इस case में क्या हो गया? जो like your VA, that was more positive for 120. After that, your B is becoming positive, and C was on the negative portion. C was there for 60 degrees. Again, C is coming for 60 degrees. So this one will be your VBA. Is it? VBA. Because आप यहाँ से भी देख सकते हैं. This is your BA. That is just reverse to VAB. So वो है यहाँ भी आ रहा है. So this is how it goes. Okay. So this you have to remember here, every phase will be more positive for 120 degrees, and then the next phase will open. After this, let us just draw the switching diagram. So I've drawn this switching, and here in this case, first initially zero switching, in the sense our T1 will be fired. Our T1 will be fired here, T2 here, and T3 here. So this is zero switching. In the sense you are switching at that instant, like the zero crossing of two phases. Like how will we choose this? In case of a phase voltage, say you are doing it practically, what you will do, you use a zero crossing detector. Okay, and you will just see that when two phases cross each other. So when two phases cross each other, in case of phase voltage, it will be 30 degrees. In case of line voltage, at 60 degrees. This is at 60 degrees. Here, two voltages are crossing. Here you can see at 60 degrees, two voltages are crossing. So that will be the initial point, that is a 0 point of firing a thyristor. Because we doesn't know, we are turning on the supply. How will we know when to start? We are starting at some other instant, the supply will be at some other. So you have to use zero crossing detector and find out when two thyristors are, two voltages are crossing. So in case of line voltage, it is at 60 degrees, that is meant to be zero firing. So here, first we will be firing a thyristor T1 at this instant. This is your T1. Okay, and this point, that is 120 degrees, because each thyristor, when a particular thyristor in a particular phase is fired, it remains positive until the phase, say A phase is more positive. A phase is more positive in the sense A is more voltage and the other two are little less. So when the A is more, the thyristor which is connected to that A will also be forward bias. Okay, so similarly here, say when the T1 is connected to this A phase, so you can see here until this A is not less, that is A is more positive here, T1 will be on. After that, after 60 degrees, you know, T2 will be on. So here, that is T2 is in the lower arm, so I am just given it in the lower. And after this here, after T1, it is the positive group, sorry, not the positive, the upper group, you can see it is T3. After T1, it is T3 will be on, and again after 60 degrees, your T5 will be on. I think you can understand this. Okay, why we have not kept T1 and say, one more thing you have to remember, this T1 and T4 will not be fired at the same instant. If it is fired, it will become a dead shot. And we know that in the upper arm also, one thyristor is there, the next thyristor will be turned on after 120. That is, each thyristor in the upper group will be on for 120 degrees. Say short kaise hoga, say ab T1 on hai, okay, and similarly your T4 is also on. So in some instant, it may become a short also. से आपका लोड बहुत कम है, सोचो कि आपका लोड प्रॉपर नहीं है, so there is a chance. I'm not saying every time it will get short, but there is a chance. It depends on the load also. Say here there is a load, but sometimes say your load is very less, so there is a chance of getting short. No, here I have drawn, 1 second. It will. No, in books also it is directly given. That's why we give something called dead band. Always we give something called dead band in practically also, that is there, because without that, why we in practically also we use this. And every thyristor, 0 and 180 firing is never possible. Okay. नहीं, आप just देख लो कि current से ऐसे flow. Say when it is short, I'm saying, say this is also short. Okay, and no, if it is star here, neutral is there. Sorry, grounded. Say by chance you have turned on this also, and this is by mistake you're turning it on. That's why they keep two different. Then in that case there will be a short. So there might be possibility. That's what I'm saying. It's not real as such, but there in this case. Say, say आपने fire कर लिया. Fire at the same. So usually say T1 and T4 you're firing. T1 and T4 are firing. T1 and T6 you're firing. Okay. And T4, by some mistake, it is fired, then there will be. So there is possibility. That's what we say. Yeah, then there is a return. But that's what I say. There is a possibility. Because these thyristors, we are not firing after some seconds. in 50, like 50 cycles per second. There are 50 cycles per second, and in one cycle itself, you are firing it so many times. So just think it is in milliseconds. So, and thyristors, you know, it will not get turned on at one instant. All the electrons also should be flushed out. Okay, so when they are firing at very high switching frequency, and power electronics application, they fire at 10 kilohertz. It is not 50 hertz also. They fire at very high. So there is a chance. That's why, like, because otherwise unnecessarily in practical circuit also we don't go for delay and all. There is a chance for dead short. Okay, so dead short is also available. So here, this T2 we saw. So this will be your T4. So this is your T6, and here again you have T6, and this is your T5. So this is the general firing circuit. So you can see here T5 and T6. So you can just see what is T5. This one is a T5, and this is your T6. So in this case, you see this is VC. आपका voltage यहाँ जो T5 is connected VC, and T6 it is connected B. So your voltage is VCB. आपका जो voltage है VCB अभी exist होगा. So what is your VCB? This point, the red one which you can see here. I can just draw it in blue and show you. So this is the VCB. So until the 60 degrees, this VCB is on. After that, T1 and T6 is on. So what is T1? This A, and T6 is your this arm that is connected to B. So your voltage, what you have to see, VAB. Is it? T1 is A, and this 6 is B. So VAB you want. The next voltage VAB. So from this point to this point, you can just track this. This is your VAB. Okay, so this is your VAB. Similarly here, T1 and T2. So this is your T1 and this is your T2. So T1 is A and T2 is your C. So VAC. So VAC is this voltage. Okay. So similarly, when you go on plotting, this is for 0 degrees firing. When you're firing T1 here, T2 here, T3 here. So this is how you get it. This is the voltage. Okay. Now the same thing, I am just firing, I'm just giving a delay of say 60 degrees. Okay. So when I do 60 degrees, I'm shifting all the thyristors by 60 degrees. So let me fire my T1 here. My T2 here, sorry, T3 here, and my T5 here. And this full thing will be my T5, is it? Similarly, from here, every 60 degrees, it will next thyristor. So here T1, so after 60 degrees, this will be your T2. And after T3, here it will be your T4. So 120 degrees apart here, this will be my T6. And this will be my T4. Is it? Starts with T4, then T6, then T2. So this is how this 60 degrees. This is when alpha is equal to 60 degrees. So now just see T5 and T4. So this is your 5 and your 4 here. So 5 is C and 4 is A. Okay. So it is CA. So you have to just see where is CA. CA is this one, is it? CA. So CA is, this is AC. So CA is just opposite to that, this one. This one is your CA. Is it? This voltage, this waveform. Say this is AC. We want CA. So just opposite to this AC is this one. So this voltage you get initially. Okay. After that, 5 and 6. So 5 you just see, this is C again, and 6 that is B. So CB you require. So CB is BC ka opposite hai. So this one. So you get 1 second, I'll just change the color. I think you can see this. So when it is 60 degrees, आपका जो waveform है, it will become like this. So AB is positive. This voltage is also positive. Okay, this voltage is also positive, but like clip voltage. Before it was like this, and here this is the voltage you get when it is 60 degrees. Now if it is 90 degrees, how will you get when it is 90 degrees? So for 90 degrees, you can see here, your voltage will be something like this. जो red में मैं draw कर रही हूँ, that is same thing. You shift the firing and you just try this. So you will get something like this for 90 degrees. So in 90 degrees, what happened? You have a positive and you have a negative. They get cancelled. So at 90 degrees, your voltage is 0. Okay. Now you just go for the next. Next is nothing but your 120 degrees. So 120 degrees. For 120 degrees, you will get a voltage like this. Just जो 60 degrees draw किया है, उसका just opposite में आएगा. So you will get a voltage like this. So at 120, what happened? What happened at 120? The voltage is negative. आपको जो average voltage negative हो गया. So same way 180 degrees. ये जो firing in 180 degrees shift कर लो. In that case, when you see, your voltage will be just opposite to your 0. Okay. Yeah. So A है negative. But हमने एक केस पहले बताया कि थायरिस्टर तो यूनिडायरेक्शनल है, करंट तो एक ही डायरेक्शन में जाएगा. फिर कैसे वो सप्लाई पावर सोर्स पे कैसे आएगा? Thyristor is always unidirectional. Here only one thyristor we have put. We have not put two thyristors anti-parallel. So here, when it will act as an inverter, आपने firing change कर दिया. Firing 0 to 90 degrees, it will act as a rectifier. 90 to 180, it will act as a inverter. At 90, it is a turnover stage. Okay, it is just a turnover stage. So all the cases, positive or negative, दोनों case में current is always unidirectional. In first case, 0 to 90, your voltage is positive, current is positive, your power is also positive. It flows from the source to the load. Second case, current is positive, but your voltage is negative. आपके यहाँ हमने 120, 180 करते voltage negative हो गया. So negative into positive, your power is negative. So it will flow from your inverter, like load to your source. So in this case, load should be capable of having some energy. उस लोड के पास एनर्जी नहीं, रेसिस्टिव लोड डाल दिया, you cannot expect that will give the source. So your load should be, say, some traction application. Mostly when you go down the hill, they say it supplies power back to the source. Or you have some inductor or in the back EMF of a motor. So that can supply back to the source. So this is a basic concept of a converter. By changing the firing angle, you can do all these magic. Okay, so here same thing for a DC circuit. I can just show you a dual converter. So almost the time is up. So I am just telling you a dual converter. So वहाँ भी voltage source converters आप देखते समय. So whenever you see a dual converter, you have converter 1 and 2. In the sense two circuits like this. जो rectifier मैंने बताया. वो रेक्टिफायर दोनों साइड में है. सोचो कि इस साइड में भी है, इस साइड में है. दिस इज ऑल्सो 3-phase रेक्टिफायर, दिस इज ऑल्सो 3-phase रेक्टिफायर. सो दिस रेक्टिफायर, one rectifier which is this side, can either act as a rectifier or an inverter. Similarly, A भी कर सकते हैं. So when here, say the total angle for both what you give is alpha 1 plus alpha 2 is equal to 180 degrees. So just imagine I am giving 80 degrees here and 100 degrees here. So 80, this will act as a rectifier. So ये AC को DC में convert करके यहाँ दे रहे हैं. Or this will act as an inverter. वो क्या करेगा? In this case, what will happen? This act as a rectifier. Okay, AC को DC में convert कर रहे हैं. और this side, this DC को AC में convert करके यहाँ देंगे. Okay, so in this case, it is alpha is 80 degrees and here it is 100. Just reverse कर लो. यहाँ आपने 80 दिया और यहाँ 100. Then this will. So it is vice versa. It depends on what is the angle at which you fire. Alpha 1 plus alpha 2 is equal to 180 degrees. So here it is shown rectifier, inverter, converter 1 and converter 2. Just I'll show you, this is I'm just going to show you a dual converter. So where, so here you can see here, this is a dual converter. And in this dual converter, we are using a DC motor. So here one bridge is shown here. This is one bridge and 4 thyristors with another bridge with 4 thyristors. So this and these 4 bridges are controlled using 4 thyristors here, and these 4 bridges are controlled using these 4 thyristors. Okay, 1 second. This is a single phase. Okay, jab simple example ke liye humne liya. Here there are 4 thyristors. Here there are 4 thyristors. This is one. I showed you in dual converter. 2 converters are there. So now these 4 thyristors, as I already told you, this is a power circuit. जो motor and power circuit है, और ये control circuit है. So इस दोनों को isolate करने के लिए they have used 4 MOSFETs. Sorry, optocouplers here. These are the 4 optocouplers for this these 4 MOSFETs, and these are the 4 optocouplers for these 4 MOSFETs. Okay, and here as I already told you, यहाँ 2 टर्मिनल जो दिख रहे हैं, ये एक टर्मिनल, इस टर्मिनल में हमने मोटर को कनेक्ट कर लिया और दूसरा टर्मिनल में हम एसी सप्लाई दे रहे हैं. इस टर्मिनल में एसी सप्लाई दे रहे हैं और इसमें हमने मोटर को कनेक्ट कर लिया. सो एसी सप्लाई देने भी डायरेक्टली उन्होंने क्या कर दिया कि जो 230 वोल्ट एसी आ रहे हैं उसको एक ट्रांसफार्मर से कम करके यहाँ अराउंड 12 वोल्ट एसी ही दे रहे हैं, उसको स्टेप डाउन करके यहाँ से वायर जा रहे हैं, इसको यहाँ दे दिया. सो यू आर गिविंग 12 वोल्ट AC supply here, and you are taking this here. This whole circuit can be replaced for a higher model also when you're making it for a thing. And here you have a MOSFET, okay, and this 2 switches are given. Sorry, MOSFET nahi hai, I'm sorry, microcontroller. And here you have 2 switches. One switch is just for switching, like say 90 degrees leke aa gaya, dono off ho jayega, and then you can switch on from one to another. So uske liye ek switch rakha hai ki first aapko isko operate karna hai or otherwise isko operate. This case में all the 4 quadrant operation are possible, but here they have shown 2 quadrant, motor forward and the motor reverse. Okay, for first and third quadrant operation are shown here. And यहाँ नीचे एक switch देख सकते हैं, उसको press कर दिया तो you can change the firing angle of these thyristors. So इसके firing angle change करते समय motor का speed हम change कर सकते हैं. Forward direction में भी motor का speed change कर सकते हैं, reverse direction में भी motor का speed change कर सकते हैं.
And currently DC motor 230 volt job for easier compressor.
So now it is 90 degrees. So now you just saw this. So this is the same thing. If it is a fax device, anything, you use MOSFETs here. So you require an optocoupling. Okay, here driver is not required because it is not, MOSFETs are of very low voltage, so it can be driven. But sometimes you have to use, when you go for higher rating, driver ICs are also required. And this is how, like by changing one, they're saying it is pushing the button. Actually, when you're pushing the button, you're changing the pulse rate to the thyristor. So actually firing angle is changed. So automatically the speed is controlled there. 90 degrees. So when you're changing, it is the center thing, that is there is no voltage. So you can just shift over to the other stage. Okay, so this is the same way. There also in fax devices also you can see the voltage source converters are used. By changing the firing angle, you can make the exchange of real and reactive power there. Okay, based on what type of load, like the capacitor or inductor or something will be connected, and it can be done. So is there any doubt in the centers? I think at 1 o'clock, many of them have left. This is just DC I've shown you, but the same thing can be possible with AC also.